tentative in the sense that the details are written on sort of handwritten sheets of paper. So until it's written up, I don't feel safe to claim it. But let me mention also that I think the result is true, and at least I want to tell you what the strategy to prove the result is, and to state a theorem instead without quotation marks, and give a proof in a baby case. Okay, let's see if this works. Okay, so what is the theorem I'm referring to? So the classical theorem of Narasimhan and Seshadri says the following. So we take X, a Riemann surface, and we take small x a point, and we take a representation of its fundamental group. Then to this, you can associate a vector bundle. Which is actually defined as you would expect. So you go to the universal cover, and you take on X tilde the trivial vector bundle of rank R, and then you have a diagonal action of the fundamental group on X tilde and on this trivial vector bundle, thanks to this thing here. So you take phi lowest star of X tilde to the R modulo, and you take an invariance for this for the action of this fundamental group, and it's a locally free sheaf, etc., etc. Okay, and now the theorem of Narasimhan-Seshadri characterizes semi-stable vector bundles, in fact, stable vector bundles on Riemann surface X of degree 0 in terms of this representation. Okay, then so let's E be a vector bundle on X. E is isomorphic to how do I want to phrase it? Okay. Or maybe let me say this E rho is stable. So let me phrase it in a way that then I can sort of generalize this question also to the p-adic setting. E rho is stable if and only if this representation rho in fact factors through a subgroup, which is that of unitary and irreducible. It's if and only if rho is unitary and irreducible. Semi-stable, sorry, of degree 0. And every stable vector bundle of degree 0 arises in this way. Okay? So that's the... Yeah, some up to... yes, yes, yes. So it's, yeah. Okay, so that's the question. And now we pass to the p-adic setting. So the theorem is from 65, and even to phrase these questions in the p-adic setting, we have to wait a little bit. So the question has been raised by Faltings in I think 2011 or shortly after. So it's the following. So I need to set up some notation. So first of all, instead of working over complex numbers, we work over a local field. So we take p prime. It's the same p. We take kp inside k, a finite extension. And that's crucial. For the whole story, that's crucial. And it comes from the fact that at some point you have to count objects classified by points of modular spaces over residue fields. And then if the field is finite, you know that you have finitely many objects. Okay? So the fact that you have finitely many objects in characteristic P plays a crucial role. So you have a finite extension, and then I will denote V, the ring of integers. and then little k, the residue field. And of course, I also fix an algebraic closure. And then this has a p-adic topology, so I can also complete. It's what I call CP, the analog of the complex numbers in this case. And then I have V bar inside K bar ring of integers. And K bar, which is simply F V bar, the residue field. Okay, so this for the setting. And then I want to take C, which is smooth, projective, geometrically connected curve over V. And I fix also X a section of C. Everything I'm going to say actually is insensitive to finite extensions of K. So the fact that there's a section, it's not crucial. And then so Faltings is able to associates to a continuous representation rho. So here we, instead of having the usual fundamental group of the Riemann surface, we have the geometric fundamental group of C, which with its profinite topology. So also every time I put these decorations underline means that it extends scalars. It's the p-adic topology. This is the profinite topology. So associates to a continuous representation rho a Higgs bundle. Sorry for my handwriting. Higgs bundle. E rho theta on the base change of the curve C to CP. So yes. I'm going to mention this. So, but let me first state the result. So E rho is simply a vector bundle, so locally free sheaf on CCP. Okay. Considered underlying analytic space or as an algebraic object doesn't matter. Everything is algebraizable, even if you are over CP. And theta is a Higgs field. So it's an element in the endomorphism of E rho tensor omega 1 of CCP. So these are the linear endomorphism. Okay, so this is the pair. Okay, and as Francesco scooped me already, so this part, as this is the beginning actually of a rich theory by Simpson.
What fundamental group is that?
This is the algebraic fundamental group. Yes, the profinite, usual profinite, yes. So the profinite completion of that thing. Yeah. But it's important that this is continuous, so these topologies are respected. So this part, so as this is at the beginning of a theory that Simpson vastly generalized for higher dimensional varieties, and then there is the spectral variety, and so on and so on. The same thing actually has been done in this case. So this is part of the so-called p-adic Simpson correspondence. And so since now I'm recorded, I have to mention all names so that people don't get offended. Okay, so this was initiated by Faltings, and actually this is a very short paper in Advances in Mathematics where some of the details are a bit hard to follow. So this has been streamlined by Abbas and Rowe and Suji. And recently, actually, this has been recasted in the language of Schulz's perfectoid spaces, okay, by Ben Hoyer. I hope the spelling is correct. And actually, I don't know how if the gospel of perfectoid spaces reached Pisa and how familiar you are with these objects. Not much. No courses. Okay. Okay. So this is just to convince you that you should invest in this. So a way to recast the result in this construction is actually very close to what we have there, because actually if you take your curve C over CP and you consider as an analytic space, then that universal covered over there, which makes sense in the complex setting and it has a complex structure and so on, can be constructed using Hadik spaces, and it provides a perfectoid space. Okay, so you can make sense of this map, and not only this universal cover of CCP analytic has a structure of a perfectoid space. Okay, and you can use this plus Tate-Sen theory to actually prove this result, which I think is a very nice application, a very nice way of rephrasing. I think in a very clear and clean way what Faltings has done. So that's yes.
And in this pianist setting, the statement is also was for Simpson. Simpson was a statement about modular spaces, right? So it was like
That's
modular spaces and so on.
So that's okay. So that's the how Hoyer tries to phrases the thing. Okay, and in fact that was my first attempt to prove the analog of this result. There is a caveat though that the modular space, for line bundles of degree 0, the modular space that you get here, even for X field 0, is actually the completion of the Jacobian at the close points in characteristic P, which is no full object. Okay, so for example, the way Narasimha Seshadri proved the result is using modular spaces and proving that certain map is proper and so on and so on. That will not extend in this case. Okay, so it can be phrased in terms of modular spaces, but actually this is not as rich as a rich theory as one would has in this case. Okay. Yes. Yes, you have a spectral curve, and yeah, you have all those gadgets actually has been worked out very nicely by Ben Hoyer.
So that universal cover, I mean, there is a universal cover as a speed, right?
Yes, yes.
And is that,
so you have to analytify this construction. It is a perfectoid space.
Yeah.
So that means that you have a.
You start from the standard.
Yes. Yes. And the fact that it's perfectoid, it's not simply an extra word that you can add to this construction, but it allows to descend things. So to do this, okay, it allows to make sense of this and see that you can sort of descend to a locally free vector bundle. And here it's where this perfectoid property plays a crucial role. Okay. Yeah. Okay. Very good. So that's the advertisement for the gospel of perfectoid spaces. And around the same time, actually, there was work of Denninger and Werner, who said the following. So they start with the E, which is a vector bundle over CCP, such that, so here's the assumption, there exists a finite and étal cover dk bar of ck bar there exists a model D of dk bar over V bar, okay? So usual property, proper and flat. Actually, I don't even need semi-stable reduction, okay? So something in characteristic 0 that I can extend, okay? Mind that there are many covers of degree P in characteristic 0 which are finite et al, and they would not extend to finite et al covers of C, okay? So here there is a mess going on when you start trying to construct models of covers in characteristic 0. It's not finite et al, okay? That's the point. That's the point. And even not finite, okay? Id est D over C V bar proper and flat over V bar. That's fair enough. Okay? And a model E of the pullback, model E as a vector bundle over D of the pullback of E to dk bar. Okay, so I have my E, I pull it back, and I assume that it extends to a vector bundle over D. There is such that, but don't. This youngster so impatient, right? And here's the strong request is that if I reduce my E down to K bar, I want this to be isomorphic to O of D, the special fiber to the R. Okay? So I extend it as a vector bundle and I assume that on the special fiber of D, it's just sum of copies of the structure sheaf. Okay? So I call this, so vector bundles that satisfies 1, 2, 3, from now on, Denning-Werner vector bundles. This is a nice category, it's closed under tensor product, and so on. Yes, it's a vector bundle, generically. But on the special fiber, it's a sum of copies of the trivial bundle. The special fiber. This is the little k. This is a little k. Yes. So I started with a vector bundle. I pull it back here. I assume it extends over this model for vector bundle with the property that on the special fiber, so here, it becomes trivial. Not generically. No, not at all. Not at all. Okay? So these I will, from now on, denote as Denning-Werner vector bundles. In short, okay? And then for any such, they construct, meaning Denning-Werner, a representation rho of the fundamental group
without any condition of the
no,
EW vector bundle?
no,
Stability, no.
no, nothing.
But this is automatically semi-stable or stable with respect to some stability conditions, since there is this duality.
I will not answer to this. So, impatient youngsters, I mean, they shouldn't be allowed to speak. Right? And then Daxing Su actually related the two constructions, Faltings and Denninger-Werner, and he proves that the Denninger-Werner construction is the inverse of Faltings for Higgs bundles with the Higgs field with 0 Higgs field. In the sense that, if you take this representation and you feed it in Faltings machinery, that would provide an Higgs bundle with trivial Higgs field, okay? And vice versa, any, so if you take a representation, okay, you construct this Higgs bundle and you assume, and you get that the Higgs field is 0, okay, then the associated underlying vector bundle will be one of these Denninger-Werner vector bundles, okay? So this Denninger-Werner hypothesis of potentially trivial reduction characterizes exactly the image of Faltings construction in the case of the Higgs field is 0, okay? And then coming to Francesco's question,
You're saying the E row is
yeah, so you start with an E, you take this row, and then you construct your E row, you get E. Yeah, exactly. Yes. Okay. Now the conclusion is that so once you have a model, okay, like this, you can always make it semi-stable, and then this will be this vector bundle on the special fiber will be semi-stable of degree 0, and it will be of degree 0 component-wise. So for a suitable choice of a polarization on the reducible components of the special fiber, it will be semi-stable. And then you know that semi-stability behaves well under generalizations. So this condition implies that if E is a Denninger-Werner vector bundle, then the pullback to dk bar is semi-stable. And well, also the degree is preserved under generalization, it's of degree 0. But then in characteristic 0, you know that semi-stability behaves well under finite total maps. So you deduce that E itself over CCP is semi-stable of degree 0. So you see that we get one direction of the Narasimha-Shastri theorem. And of course, now the question is any semi-stable vector bundle of degree 0 constructed in this way? Okay. So let me write the question. No, because this has degree 0 on the special fiber. So if you pull back E, so the pullback of E to dk bar then has also degree 0. I mean, it's a vector bundle on a smooth curve. You take a smooth cover. If the pullback is degree 0, then the original one has to have degree 0, because the degree is just multiplied by the degree of the map, which is 0 afterwards. It has to be 0 beforehand. Numerical degree. Yeah. Nothing fancy. Yeah, I'm a simple-minded person. Too naive. I'm a naive person, so it's really the numerical degree. Yeah, numerical degree. Yeah, so that means in this case of degree 0, okay, that if you take any sub-vector bundle of E, okay, that will have a degree, okay, and then E is semi-stable if and only if every of degree 0, if and only if every sub-bundle must have degree less or equal to 0. Okay, you cannot have sub-bundles of positive degree. Okay, so this is nice because these semi-stable vector bundles, or the stable ones at least, come in a moduli space. So you have families, you can study them. Okay, So they're nice objects among vector bundles. Okay, so let me write the question. So I'm going very slow. Sorry for that. Sorry? Yeah, but I mean, this is a history of mathematics. It's nothing new. Okay, so the question raised by Faltings. Someone says conjecture, but it's not, in fact, a conjecture. It's a question he asks. Is every semi-stable vector bundle of degree 0 on XCP Denigan-Werner vector bundle? Okay, so that's the converse of Narasimhan-Seshadri question. So
Yeah, the X is the same as the C.
I knew I shouldn't have introduced Riemann surfaces. Messing it around. Okay, and there are, so the examples we know. So genus 0 is fine, genus 1 is fine, and line bundles is fine.
If I understand correctly, that condition somehow increased.
Yes, yes, yes. Which I think is correct, because it's telling you, I mean, this gives you an integral structure with some sort of trivial reduction on your vector bundle, and this serves as a unit ball in also in your representation. So a lattice in the CP representation, if you want, which is replacement for the unit ball for a unitary representation. So I think it's the correct analog. Okay, thanks. Okay, and what I would like to have proven is that actually this is not the case. So the question is a negative answer. And let me explain why.
But in genus 1, you do explicitly how you prove it.
Yeah, I mean, you can classify vector bundles. Yes, yes, yes.
Zero is trivial.
Yes, yes, yes. I mean, it's a sum of line bundles, you know, the case of line bundles, and then. Okay, so I want to first of all, an interlude.
You're saying that in this example, the answer is positive.
It's okay. Yes. So interlude is the following. If X is a smooth projective curve, so also over K bar connected, okay, and F is a vector bundle on X, so, and we let Frobenius, the relative Frobenius may be denoted by phi, and we say, so this is the definition, we say that F is strongly semi-stable if F and phi alpha star phi m alpha star of Fm, so this means that you iterate this construction, is semi-stable for every m. And now there is a relation between this condition of strong semi-stability and being trivial after some finite extension equal to CP, which has been proven by Lange and Stuhler. So F vector bundle on X of degree 0, then F is strongly semi-stable, if and only if there exists gamma from y to x, which is finite and flat, such that the pullback of f is actually isomorphic to OY, to some R, okay? And here you definitely need that discover is not at all. Okay? You need some inseparable map to be able to realize this.
But you need that base of the curve.
I think not. I think not, but I'm not sure. Yeah.
How do those models apply?
So in this case, since we are working over sort of finite field, essentially, yes, because you have a semi-stable,
That's over the closure of
Yes, but still, everything is a finite type, so it's defined over a finite field, and then
yeah.
usually
No, I wasn't thinking it would be false curve.
yeah. But here it's true, and actually it's a good point about why semi-stable vector bundle is useful. There's a moduli space for semi-stable vector bundles of degree 0, okay? And then you see, if you start floating around with Frobenius, you have a point in your moduli space, and you are having an orbit of it defined over the same field, and then you hit it back at some point because you have finitely many points. And then you get exactly this Norris finiteness. So you see the power of having moduli spaces. It's here, okay? Okay, and here I don't know how to state the result, because as I said, until I had all the details written up, I don't want to claim it, but so hope, expectation, maybe frustration. I don't know, depending on the day, is that if R is equal to 2 and P is bigger, so assume that, so G is the genus of C and is bigger or equal to 2. So you want this to be bigger than G minus 1. And if I have E vector bundle on CCP, then this is Denninger-Werner, so potentially after a finite extension, it has this model where it is trivial. If and only if he has a model E over C OCP such that the reduction, so remember this is a smooth curve, so there's a moduli space even mixed characteristic, so you extend this vector bundle, a vector bundle, and we want that this is actually itself strongly semi-stable of degree 0. So this potential requirement of Denninger-Werner actually should imply, I think, this strong semi-stability already of the curve itself. Okay, so of course from right to left it's a triviality. So the difficult part is to prove from left to right. Okay. Then in this case, actually, at least for vector bundles of rank 2 over smooth curves, there is a literature that studies the difference between semi-stable vector bundles, strongest semi-stable vector bundle, and so on. And then we know that there are semi-stable vector bundles with degree 0 on the special fiber of C, which are not strongly semi-stable. You take one of those, you deform it to characteristic 0, and then you get an example of a semi-stable vector bundle in characteristic 0, which is not Denninger-Werner, and this would provide a counterexample to our negative answer to the question of Fatex. Okay, so let me write this. so Herbert Lange and Christian Pauli. So they proved that in the moduli space of semi-stable vector bundles over the special fiber of CK bar, vector bundles of degree 0, there exist points corresponding to non-strongly semi-stable vector bundles. And this, again, a very geometric construction. You use Verschiebung on the modular space, and actually that's a rational map, and you take the base locus of this rational map and you prove, so you can even get the dimension and, you know, get a very explicit hold on what this locus is. And so then, so take such a vector bundle, which is not strongly semi-stable, but it's semi-stable, and any generalization to C OCP, and then taking the generic fiber, would provide a negative answer to Falting's question. Okay? So
This would probably say that the right moduli space we consider is the one of strongly semi-stable vector bundle.
yes, yes, which is yeah. It's not a modular space. It's not an yes. Yes. Yes.
It's not about this one.
Exactly. Which, I mean, exactly as I said, you see already in the line bundle case where already this question doesn't, I mean, appear already. If you want to insist of doing things on modular spaces, the modular spaces of the line bundles that you get are the following. It's the disjoint union of the completion of the Jacobian at the closed point in characteristic P, which is a disgusting object for people doing algebraic geometry. It makes perfectly good sense in the case of adic spaces and so on. And I think this strongly semi-stable condition has the same ugly.
This was not this, I mean, this was no longer that was like the moduli space. The one
Yes?
it didn't cost, I mean, I'm not.
No, 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 no.
It didn't cost
No, no, no.
the moduli space,
No. No, no.
I mean, I don't think there is a notion of a family.
Exactly. It's really a pointwise.
You can see a single one.
Exactly. Exactly. As for line bundles, we said you really have to reduce and to a single object, and you can work only locally around that. It's the same kind of principle.
So when you say any generalization, question whether
You can always, right? This vector bundle is given by a cocycle, you lift it. It's a cocycle for GLF.
So that would give
I mean, I can certainly construct one. Okay. Simply by representing this by a cocycle for GLR, or intersection of two affines, and then you lift it. Yeah, exactly. Okay. Okay, so I don't think I'm still in the history of mathematics, but so I wanted to tell you why this where these two hypotheses come from. Okay, so
I mean, they would refer if this is true that
Yes. I want this. Yes. So concerning hypothesis 1, so suppose that
So this open expectation frustration is really for R equal to for larger R.
I think it should be true in general. So let me tell you what the general statement should be. So for every R and for every, I mean, R bigger or equal to 2, and then P should be bigger than R minus 1, and G minus 1, then I think the same result should be true. Okay, so the hypothesis 1, so if E is Denigan-Werner and rho is pi 1 of ck bar, xk bar to grcp, the associated representation, then since CP is a Bezout ring, okay, it actually admits a representation in OCP, so you can reduce it, okay. So I take this residual representation, okay, and actually in the R equal 2 case, rho bar restricted to inertia has a billion image because you have a P group, pro P group represent. So what is this inertia? Okay, so this classified covers of CK bar. Of course, you have the covers that extends to finite file covers. Okay, and that defines a quotient group, and then you have everything else. That's the inertia. This has a billion image, so that's one thing that you will see appearing. And then actually, thanks to this, thanks to the fact that also the abelian universal cover of C is a perfectoid space, you can actually prove the following. So invoke perfectoid spaces, they will appear and save your day. And then you can prove actually that you can find covers in characteristic 0 and models so here it's so I want this to be finite étale Galois. I want this to be finite étale Galois and abelian. Okay, so here I have a G0 acting, and then I have a group G acting, and I can find this to be having semi-stable model. Okay, and then by uniqueness for semi-stable model, this group G would act on it, and you can take the quotient, and then Renault proves that the quotient is again semi-stable. Actually, here you can take this stable model. You can mod out, this will be only semi-stable. You will be, in the cover, you will have the P1s sticking out, okay? And also the quotient here will be semi-stable. So now, first of all, we have sort of nicer category of curves to work on. And also, there exists a model En of the pullback of E to C and K bar with compatible action of G. Okay, and I want to show then the argument how to conclude in the case of the abelian setting. So what I'm stuck with the combinatorics is exactly this extra innocent everywhere et al. Galois thing. Okay, so I hope I will be able to. I have tons of examples that I worked out where it works. So I hope there will be actually a general theory that allows to get rid of the problem. Okay.
Could you repeat what the inertia is?
So the inertia in this cover is exactly this. So this is the maximal extension. This is the maximal cover that extends to a finite total everywhere object. Okay, and actually here also you can define the maximal quotient that corresponds to covers that are exactly. Okay, and actually thanks to this, and for R equal 2 is always true for any residual representation, I can assume that this is a billion. Okay, and now the strategy. Yes. So if you take the maximal abelian cover, this is perfectoid. Okay, so the fact that the image is abelian, okay, tells you that when you restrict to the kernel of this row to the kernel of the abelianization, okay, of this. So suppose this is trivial, okay, for the moment. So you restrict that to the kernel of the map to the maximal abelian quotient of that fundamental group, okay. Then the fact that this is trivial tells you that the corresponding representation modulo p is trivial. Okay, so that tells you that the cocycle defining this thing is trivial modulo the maximal ideal of OCP, hence modulo some small power of P. And then if you go up along this tower, since it's perfectoid, you have actually elements of smaller and smaller traces, okay? And you take an element, you take an n large enough so that you have an element with a trace which is smaller. The p-adic evaluation is smaller than the power of P that annihilates this cocycle. And that allows you to trivialize the cocycle defining the vector bundle. And then you can descend to an abelian cover. Okay? So there exists a model, and sorry, it's a model with an action of G, and, sorry, such that, again, En tensor V bar, K bar is strongly semi-stable. So I'm not assuming anymore it's trivial. It's strongly semi-stable of degree 0 and even degree wise on every reducible component. It's of degree 0. Okay, and now the strategy is to prove the following. So you have your En, and I have my pi here. So I define F to be pi lower star of En stabilized by G. Then I pull it back. This, of course, maps to En by adjunction, okay? And I want to prove that delta is an iso, okay? And then this is still a model. This is a model of E on C OCP. And since if we prove this, the pullback is strongly semi-stable, so also the special fiber has to be strongly semi-stable, and we're done. Okay? This implies okay. So that's sort of the use of hypothesis 1. And now we have hypothesis 2.
The theorem is the
Yes, yes. Implies hope. Yes. And instead, I want to tell you, so theorem is a true theorem. Assume, of course I erased. So we had this residual representation, rho bar. So assume the image of rho bar is a billion, which means that in this argument, I can prove the claim in the case that these two are equal. Okay.
Sorry, the word you just erased. So the assumption that R,
So
you assume that the restriction to inertia was, or
no. So we said CP is a Bézout ring. So there is a lattice. You reduce it, and then if you restrict to inertia, okay, you can put, since it's a Propy group, you can put it in the Borel of GL2. So it's trivially a billion. So that's why. So I don't need this assumption that inertia is a billion. I mean, inertia is a billion is, I think, enough. But for R equal, I mean, I hope that it's the right condition to prove this. And for R equal 2 is automatic. That's what I wanted to say. Okay.
previously you said that for general anything, but then you don't have this theorem.
Exactly. So this is even more sort of a dream. Okay. So yeah. Okay. So you assume the image. Yes. Yes. So the image of rho bar is a billion. It has in the picture above C0 k bar is equal to ck bar. Then the claim holds true. So that's the evidence that so far I have. Okay. So that this is really, so that's the claim. Okay, so let me prove it in a baby case. Okay. So there is a very beautiful theory of Renault that tells you how the dual graph of the reduction of Cn looks like. That's a tree. It's a tree, and so there is a central point corresponding actually to a curve which is isomorphic to C, okay? And then, which is the central point, it's an oriented tree. So that's the starting point of your tree, of your orientation. And then while you move along the tree, okay, so for each node of the dual graph, you have a decomposition group and you have an inertia, okay? And actually, what is inertia at one node becomes the decomposition group at the node after that, okay? So there's a very nice picture of what's happening. So in particular, and the end nodes of this tree, the map down here is etal, which we're going to use. So I had a very beautiful tree, but time is short. So I'll just consider the simplest case where the dual graph of I assume that baby k is actually even n equal 1. Okay, so it's a degree p cover. So here I assume of degree p to the n. So it's a degree p cover. Okay, so the dual graph it's simply 2 points, and the dual graph of actually Cn v bar modulo g is also just a tree, okay? And here, of course, you have So one node corresponds to simply ck bar, and it also it corresponds to ck bar, and the induced map it's Frobenius, okay? And here instead you have a P1, so you have a P1 sticking out, and here actually you have a map. Let me call D, which is a separable map of degree P. Okay? And now I reduce, I think we started 4 minutes, so I have 5 minutes, right? Because you see the marvelous formula. So on these two components, I can take my E and I can restrict it to these two sides. Okay, so I have the restriction of E to D, so E k bar to D. I call it E prime, E k bar restricted to ck bar. The other component I call E double prime. And then I have the pullback of F restricted to down to K bar restricted to D. I call F prime, and similarly I pull back the pullback of this F of the claim. Take the special fiber restricted to CK bar is equal to F double prime. Okay. Now remember, I want to prove that this is an isomorphism. So we have a natural map. I have a delta prime going from F prime to E prime, and I have a delta second mapping to F second to E second. And I want to prove that this is what isomorphism. Okay? And our basic information is that since the map is separable there, the delta on D, the delta prime is injective. Since I told you that this is also semi-stable of degree 0, okay, if delta prime is not iso, then the degree of F prime must be negative, and it's of course a power of the degree, so it's less or equal to minus P. If delta prime is injective instead, so it is an isomorphism, then that implies that in particular that at the singular points, this map, and hence in a neighborhood, is also injective. And then by degrees, because these have all degree 0, and these also, since it's a model of something of degree 0, the total degree is 0, then also delta second is an isomorphism. So you see that the basic principle, even if you have a very complicated graph, you start from the boundary points where the map is separable, and you have injectivity, and then you want to prove that it's this injectivity is actually an isomorphism by contradiction, and then you get to the interior more and more and more until you cover all the dual graph. Okay, so we are left to stuck here. So what happens if delta prime is not an isomorphism? Well, so this map could be 0 then, okay, but we know that if you take the special fiber of K bar, and then we pull it back, so this F second is actually contained in Frobenius upper star, Frobenius lower star of E second. So maybe it's not injective here, okay? So here you have your map E second. But now this is a marvelous object because you have Frobenius descent for vector bundles. So there is a connection here whose kernel is exactly the phi lower star. And using this connection, you have a filtration by sub-vector bundles where the graded are E second first. The first graded is E second. Then you take the kernel of this quotient map. If you apply nabla, that maps to each second tensor the differential of ck bar, and so on. So by Frobenius descent, this has filtration with graded pieces, which are simply isomorphic to each second tensor omega I of ck bar for I0 p minus 1. So it's simply Frobenius descent or Cartier theory, but I mean, very classical things. And now this induces a filtration here with the graded pieces which are contained in here. This is a semi-stable vector bundle degree 0 times a line bundle, so it's semi-stable. So the graded pieces here must have degree less or equal to the degree of omega I. So the total degree of f second has to be less or equal to the sum of the degrees of this omega I. And so the end conclusion using that E second is semi-stable of degree 0, the degree of f second cannot exceed r times r minus 1 times, so it should be divided by 2 times the degree of the canonical bundle, so I simplified the 2 already, g minus 1. And now the total degree f prime is equal to 0. But then this is less or equal to minus p, this is less or equal to this, and we're done. Huh?
R is not necessarily two.
No. So this argument, so if you assume that you have a model on this abelian cover, actually the proof goes through. Okay. So the R equal 2 was used to have inertia, which is abelian. And yeah, so where I'm stuck is where you have this first innocent looking finite total cover that appears, where I have to still struggle with the combinatorics. But I mean, I think it's marvelous. So I'll stop here.